My name is Jackson Sippe. I'm a PhD student at the University of Colorado Boulder, where I'm advised by Dr. Eric Wustrow, and I focus on research in privacy and censorship circumvention, specifically using network taps or network vantage points. Hence why today I'll be talking about combating internet censorship through large-scale network vantage points. And thank you guys for squeezing me in here, but yeah, I'm looking forward to it. So for a little bit of background, as we know, internet censorship is a thing, right? Many countries censor their internet, and no country is truly free. Unfortunately, Freedom on the Net did not have any information on Romania, but you can see for all of these countries that they have been able to record data on that large swaths of the world are under some form of censorship. Even though countries like the US and parts of Western Europe don't show any signs of censorship in this particular measurement, there are still a number of citizens who believe that censorship has occurred. Here in the US, roughly 75% of Americans believe that social media is censored in some way. In countries like China, where censorship is more prevalent, billions of people are affected every day. We refer to their censorship mechanism as the Great Firewall, or the GFW. I will be referring to that more as we go on. Most of my research is on censorship in China, and I believe that it is sort of a precursor to what we can expect to see in other countries moving forward. Global events drive a lot of this censorship, right? Political landscape changes, such as the re-election of Xi Jinping in China, often spike censorship events in that country. We've also seen a spike of censorship in Russia as the Russian-Ukrainian war has gone on. We also know that sensors are evolving, right? As new protocols are coming out, for example, Quick, we see that they are working to adapt to the challenges that these protocols provide for censoring that form of traffic. Additionally, we know that sensors tend to be sensitive to false positive rates and network performance, right? They don't want to be responsible for network outages, and they don't want to be blocking traffic that isn't in fact something that they deem undesirable. So moving on to the forms of censorship. I know that in the EU and then also here in the US, we are becoming more and more concerned about censorship that is occurring in our own countries, right? For us, we've had a whole debacle with TikTok, a Chinese-based social media company that has become very popular here in the US, and our government has threatened to shut that site down numerous times. However, when we look at censorship like this is often what I would refer to as policy-based censorship, right? So in the US, we would legally compel companies such as Apple or Google to prevent those applications from being present in their app stores, right? And this sort of prevents the need to do any form of technical censorship. Policy censorship can take form in a couple of different ways. One can be content moderation, right? Compelling a company to implement moderation on their platform, as well as legal action, right? DMCA takedown requests are a common thing here to combat copyright, but also preventing an app from existing in the App Store, right? Now, my research focuses on technical censorship, which is kind of what I will be referring to throughout the rest of this talk. And while this isn't something that we are currently seeing in Western nations, I do believe that it's something that we can start to anticipate seeing more of, right? We've heard about the UK wanting to try and be the world's cleaner of the internet, right? But to do that, they will have to implement this technical censorship and find ways of detecting and stopping traffic that they deem undesirable. Now, there are two different forms of technical censorship. Active probing kind of being the first one, where we go out and knock on the door, right? We're going to say, hey, server on the internet, what protocols do you support? What services are you running? Things like that, right? And if we can identify services that we deem undesirable or we believe we can't control, then we can record things like the IP address associated with that host and then block it later on. The second form is passive observation. And this is when we're just looking at that network traffic going across our wire and identifying things that we deem undesirable and then blocking it. Oftentimes, you'll see sensors combining active probing with passive observation, right? You might use active probing as a technique for identifying the IP addresses associated with VPNs or proxy services, and then passive observation looks for those IPs to show up in connections, and then we'll use a variety of different techniques to tear those connections down or alter them or halt them in some way. So I'll be speaking mostly about passive observation or network observation as we move forward. And there's a couple of different tools that you can use. Some of you may already be familiar with. I'll move quickly through this, but they kind of fall on a spectrum, right? On one end of the spectrum, we have these very verbose plug-and-play tools such as Zeek. They offer pretty dashboards, notifications, not a whole lot of work on the end of the maintainer. But these tend to be bogged down by high resource demand, right? And they don't scale as we start to look at traffic at a nation state level. On the other end, we have frameworks such as DPDK, which is a lot more scalable. However, we're only seeing, bytes coming out of DPDK, and it can be time consuming to convert these bytes into something useful like TCP flows, application layer traffic, what have you. Currently here at CU, we use a custom parsers on top of DPDK for all of our research, which took years to develop. There's some exciting research coming out of Stanford, a tool called RITE that sort of bridges the gap between DPDK and tools like Zeek, and they're really useful in this research setting that I tend to operate in. They develop this framework that allows for kind of discarding of traffic that we don't care about early on, so it's still performant, while also having a variety of different parsers and capabilities available that allow us to ask questions about traffic and learn more about what we are observing on our networks. So moving on to the threat model that we think about when considering censorship. This can be broken down into capabilities of the sensor as well as the vantage point that the sensor has. Oftentimes with capabilities, we are concerned with the two most complex or available versions. The first being an in-path sensor and the second being an on-path sensor. With an in-path sensor, this is considered sort of the highest level of access, right? They are sitting as a host or in the path between two hosts, right? This could be a middle box, some type of border router, something along those lines. And the reason this is concerning is because they can simply stop traffic altogether that they deem undesirable. They could potentially manipulate traffic, insert different traffic, what have you. The on-path sensor tends to be a little more prevalent because I think it's easier to deploy and slightly more reliable, which we will get onto in a little bit. And with an on-path sensor, you don't have the ability to tamper with those connections, right? Or you don't have the ability to drop that traffic. However, you do have the ability to make connections to those hosts and pretend to be each other. And so what we often see with an on-path sensor is the injection of traffic that tries to manipulate with an existing connection, potentially tear it down, things like that. There's a third capability that is sort of a tier lower than both of these, which is the off-path sensor or off-path capability, in which the sensor can just observe the traffic, right, and can't send any traffic. This is becoming more prevalent as sensors are starting to collect traffic for machine learning training and classification to identify services that they deem undesirable. So moving on to the vantage point, we have two different vantage points that we're concerned about, the local adversary and then the state level adversary. So when we think about censorship, I often think about it in sort of this global or national sense, right? I'm concerned with a country that is blocking traffic for its citizens or in spite of its citizens. But there's also this local adversary that can exist, right? This could just be a business that wants its employees to stay focused while they're at work. Oftentimes, the local adversary is deploying some type of in-path, off-the-shelf censorship mechanism, and it makes sense due to the low amount of traffic they see. However, with these state-level adversaries, we often see a combination of both in-path and on-path capabilities, depending on what their objective is and how they want to benefit or weigh the risks and benefits of each approach. So moving on to some attacks that we often see in censorship and ways that the censor can manipulate traffic using these capabilities and these vantage points. The first is SNI inspection. And for those unfamiliar, SNI is a TLS extension called the server name indication field defined by RFC 6066 for those particularly interested. And it was added to TLS, right, the way that we secure our internet traffic, as a way to reduce the need for dedicated IPs for every website on the internet, right? Now we can allow for hosting of multiple domains at a single IP, and the web server or some form of load balancer can look at the SNI field to determine which website the client is actually trying to access. The downsides of SNI are that it is sent in plain text within the TLS client hello. Right? This creates some issues because it can be observed on a network, right? So now a censor can see what domain you are trying to access, even though that traffic is going to be secured later on. So what can a censor do with this visibility, right? Well, assuming that they are an on-path censor, which is typically where we see SNI inspection and these attacks occur, when they see some type of connection that they don't like, they will often alert, and then they will send resets to tear down the TCP flow that the TLS traffic was communicating across, right? Now, the question kind of comes up of why on path, why not just sit in path and, stop these connections? Well, we believe that, for one thing, this type of deep packet inspection can be a bit resource intensive and requires hosts or servers that exist in data centers off the path or not directly in the path. Can't be done by a router. Additionally, we believe that it improves network stability, right? If the sensor is to go down, is to see traffic it doesn't expect and error out, connections can still exist between clients and web servers, be it benign or malicious, right? So the sensor kind of prioritizes network stability over 100% uptime of their services. There have been mitigations proposed to SNI inspection. Encrypted SNI or ESNI was one of these. However, with ESNI, it ultimately got tabled, right? China and other nations were quick to block traffic that included the ESNI extension, and it was proposed in 2018 and is still an IETF RFC draft today, kind of due to this lack of adoption because of blocking in these countries. Additionally, we've seen other extensions come up, such as encrypted client hello, that are sort of offered as an enhancement on ESNI, and adoption of this protocol has been a little more accepted. So the next attack is DNS injection, right? This occurs before the TCP handshake and before we see TLS traffic communicated. And in this case, we have a client who wants to access a website, say google.com, but they need the IP address for that website. So they'll make a request to their name server, and the name server will respond with the IP address associated with Google or what have you for that client to go and establish a TLS connection with. What ends up happening here is a sensor will see this traffic, and they will attempt to inject traffic to a random IP address, a response from that name server to a random IP address, so that when the client goes and tries to establish a TLS connection, they're unsuccessful. The client will still receive the proper IP address from the name server, but because the sensor often beats the actual name server, the client will just take that IP address and use it. Why do they do this? Well, because DNS is over UDP and the sensor can't drop those packets, they have to inject new packets. So what we often see in China is 3 of these injections occurring at once. And we believe that this is for 2 reasons. One, it ensures a likelihood that one of the injected packets will beat the name server's actual response. And it also adds some redundancy so that if one of those injectors falls over, there's still a likelihood that a malicious injection will occur. So the last attack that I want to talk about is fingerprinting, and specifically protocol fingerprinting, right? So we know that we could connect via some type of encrypted traffic, fully encrypted traffic tunnel, maybe a VPN, or over some type of TLS tunnel, right? However, when this traffic is sent across the network, we see that there are patterns associated with each of those. Okay, associated with each of those different protocols, right? And the sensor can detect these different patterns and will block traffic accordingly. And so that's where our mitigations come in an effort to try to prevent the blocking of traffic as well as obscure what this traffic looks like. We've done a lot of work in this space. Refraction networking is sort of the name we use to define this, right? And we have a client that wants to access some type of asset on the internet. And there's a sensor somewhere along that path that will block that traffic if they are given the opportunity. So what we see, what the architecture of refraction networking is that instead of connecting directly to that asset that we want to access, we make a connection to a web service that exists within some type of institutional subnet or IP space. Then at that institution, we have an allied tap, right? A network observation point that we control, and it will identify that there is some type of connection that it needs to proxy. It will then pick up this connection and proxy that traffic on. It sounds like we're running out of time, so I will go ahead and call it there. But we are doing a little bit of other work in the space of trying to circumvent traffic using these network observation points. But yeah, thank you so much for your time. I appreciate it.
Thank you very much, Jackson. Questions? No questions? Well, I thought of something. Speaking of on-net sensors, Ovidiu, the previous speaker from Microsoft, wanted to show a demo, so he asked Copilot what is the recipe of a Molotov cocktail. What kind of reaction do you think was triggered with the local law enforcement authorities, and for how long will his communications be carefully monitored?
Well, that's hard to say. Hopefully he was using some type of VPN when making those requests.
It doesn't look like a VPN. It was a local Wi-Fi and the local Marriott interconnection. It was VPN? Oh, yeah, you did.
You saw that I've had a search on Security Copilot, but it was through VPN, through Entra Internet Access, our secure service edge solution that I've shared before. And one more thing, if you looked on that icon, it was the Enterprise Copilot, not the ChatGPT web browser. So my search, my content remains within my organization, is not used for training the model within the ChatGPT open model, yes? So pay attention. If you are using AI, use with M365 Copilot or other enterprise copilots, but not put confidential data in ChatGPT to train the model, yeah? So hi Jason, hi.
Okay, well, thank you very much. No other questions? If not, then Jackson, thank you again for your insights.